Convidamos o Sr. RAMSEY YAVUZ, da ROSKILL, para a sua apresentação.
Hi, good afternoon, everybody. I'm RAMSEY YAVUZ. I'm representing the steel alloys team from ROSKILL. Just a brief introduction about ROSKILL, what we do and who we are. We are a metals and minerals consultancy and research house focusing on the minor metal space. Our service lines are research, consultancy, and costs. We spread our service offerings across technology metals, steel alloys and its raw materials, electric vehicles and its raw materials, industrial metals, and also we look at the steel industry in depth. Myself, I'm responsible for manganese annual report as well as research into vanadium and niobium applications in batteries. Thank you. Hi, good afternoon, everybody. I'm RAMSEY YAVUZ. I will be presenting to you all about vanadium redox flow batteries and their application within energy storage. I'll be talking to you about the key categories of energy storage, how flow batteries fit within them, what is a VRB, a vanadium redox flow battery, their application within energy storage, and the future outlook of the industry. So just to start things off, give you a brief overview of what energy storage technologies are. So ROSKILL categorizes energy storage technologies into 5 different categories based on the type and method of energy storage. So as you can see on the left-hand side, electrochemical. So flow batteries are deemed to fall within the category of electrochemical storage systems, along with regular batteries, including lithium ion, whereas mechanical systems, which include pump hydro, dominate the market. Newer technologies that have been proposed increasingly fall in the electrochemical, chemical, and electrical categories. We also have electromechanical energy storage systems that rely on kinetic energy of a moving mass to generate electric energy. Pumped hydro solutions are the most common form of energy storage in this category and in the energy storage market as a whole. There's also thermodynamic systems that store energy through the application of heat, the extraction of heat as well, or pressurization, and release energy by reintroducing stored heat to the system, or allowing a compressed mass to expand in volume to drive a turbine. So these are the key categories of energy storage technologies, and I want to just focus on essentially what is a flow battery within the electrochemical battery area. So essentially, to understand what is a flow battery, the key aspects is flow batteries is a rechargeable battery in which electrolyte flows from one or more electrochemical cells from one or more tanks. So what we have is this aspect makes this decoupling of energy rating and power rating is an important feature of flow batteries. With a simple flow batteries, it is straightforward to increase the energy storage capacity by increasing the quantity of electrolyte stored in the tanks. The electrochemical cells can be electrically connected in series or parallel, so determining the power of the flow battery system, which is essentially the first point. What we can see also is the electrodes are not chemically changed during operation. So what we see is essentially this is a 20-year lifespan of an operation that is pretty much non-degradable. So we see that particularly for electrolytes that they will last throughout the whole duration of a flow battery. What's also important is, flow batteries also have a low carbon footprint, i.e. all components of a battery can be either recovered or replaced during the end of its operational lifetime. So just to walk you through essentially what a VRFB does and its functionality. A VRB is a battery where energy is stored chemically in different valence forms of vanadium in usually a dilute sulfuric or hydrochloric acid electrolyte. The name redox refers to the chemical reaction and oxidation reactions that are used in the VRB to store and discharge energy. Unlike traditional cell batteries that distribute electrolytes within each cell, a flow battery separates electrolytes into external tanks and pumps the liquid solution through a chemical reactor that store and deliver energy. So what we see from the schematic diagram on the screen is VRBs consist of two tanks storing vanadium analyte and catholyte. There are pumps are used to flow these electrolytes through half cells separated by an ion exchange membrane. Within the half cells, the electrolytes are chemically oxidized and reversibly convert electrical to chemical energy. The electrolytes charge within the cell is flown back to the tanks, increasing the battery's state of charge or form of valence. So what we see is vanadium redox flow batteries store their energy in tanks, and the electrolyte that the fluid transfers inside a battery flows from one tank to the other. So you can clearly see that it's much easier to adapt flow batteries to industrial scale applications without adding a lot of costs. So this is the key differentiation between lithium-ion batteries and flow batteries. So lithium-ion batteries store their energy in cells. They're relatively small and self-contained devices, but in a grid scale storage system, you would need hundreds or thousands of them in order to build an industrial scale energy storage facility. So in terms of practicality, it won't work well. So what are the key use cases of VRB projects, and what are some of the challenges that is needed by the grid that VRBs could potentially offer in terms of its capabilities and functionalities? So VRB systems are mainly used in long duration applications, typically with a duration of 4 to 12 hours. Longer duration systems offer improved economics to flow batteries and thus render their use more attractive compared to competing technologies. In addition, the bulky nature of flow batteries lends them better suited to front of the meter applications than household applications, which can be seen from the diagram on the right hand side. So what we can see is that there are some key challenges that the grid does require that VRBs are in a position to offer. I'm going to outline 4 of these for you. We're going to walk through essentially what they are. So the first one would be peak shifting and load leveling. So that basically means that it refers to the balancing out of a generating capacity over periods of low and high demand. So peak load shifting is accomplished by charging an energy storage system when the network is facing minimal loads and discharging stored energy when demand increases. So what we see is the main application for batteries is expected to be medium duration peak shifting rather than night-day load leveling. And the exception, however, are flow batteries owing to their suitability to long discharge durations. In this market, flow batteries have technological advantages over lithium-ion solutions. While the cost of a flow battery cell is slightly higher than that of a lithium-ion cell, the producers of flow batteries rely on what is suggested to be a lower installation and lifetime operating costs of the system as a whole to make their cells competitive in the market. The second key theme is grid management. Grid management basically means that all services related to the ability of the electrical network to provide reliable, resilient, and stable power throughout the grid. These can be adversely impacted by the flow of reactive power, so all of which could basically mean that there may be voltage instabilities or even blackouts within the grid. So energy storage systems could play an essential role in helping to stabilize the flow of power, and capacitors' ability to store or deliver their energy renders them particularly suited to this application. We can see that battery technologies aimed at grid management, however, have been on the rise and have been implemented commercially from 2017 onwards. So ancillary costs. What are ancillary costs? Ancillary costs relate to the services supporting the transmission of electricity from the point of generation to the end customer. The most valuable service within this category is frequency shifting. What frequency shifting means is aims to maintain the alternating frequency of the grid within its tolerance bounds. So typically this is done by increasing or decreasing the number and capacity of power generating assets. So whereas some power generating assets may take 15 to 30 minutes to become available or ramp up, energy storage resistant systems can reduce the response times to almost down to milliseconds. So that's a key aspect for what the grid requires and how VRBs could potentially offer that. Also reserve power. Reserve power is a segment which basically covers the use of uninterruptible power supply. So it relates to the provision of an emergency reserve when grid capacity is disrupted or there's a network-wide blackout. What most of the battery storage projects are for shorter term energy storage and are not built to replace the traditional grid. So lithium-ion batteries have been replacing lead batteries in this segment, however, have limited discharge time to provide enough energy to shore up a local grid for more than 4 hours. So this is a key aspect that VRBs are involved in as well. Just walking you through some of the key advantages and disadvantages of VRBs. Obviously, they offer longer lifespans in excess of 10,000 cycles. They're not adversely impacted in terms of degradation of electrolytes throughout the course of its lifetime. VRBs can be left completely discharged for long periods of time with no adverse effects and can be recharged simply by replacing electrolyte if no power source is available to charge them. So the electrolytes, if they are accidentally mixed, the battery suffers no permanent damage. Also, VRBs are regarded to have a low carbon footprint. This is regarded as a favorable technology of the future, and in terms of shipment and storage are much cheaper and more practical and simplified. So in addition to this, this does offer VRBs to be a favorable technology in this respect. In terms of some of the disadvantages, again, we see that volatility is something that is a concern for a lot of VRB manufacturers on a historical basis, where we're going to cover essentially the price volatility that was experienced in the vanadium market at the end of 2018, where price did undermine economics of VRBs. So this is something that needs to be taken into consideration when scaling up a VRB operation. We see that on the right-hand side of the screen, the VRB cell costs against other technologies is currently considered more expensive, but we see that for flow batteries, when you're moving from a 4-hour to an 8-hour system, the marginal cost is coming from electrolyte. On a kilowatt per hour basis, it's 20% cheaper to go to a 4-hour system, and another 10% to go from a 4 to an 8-hour system. So if we look at just VRBs in terms of the total installed projects to date, VRBs do actually serve a completely different structure, and VRBs are, the system will run highlighting the flexibility within the system, considering some of the key arguments that we mentioned earlier on. So load leveling, grid management, and reserve power in the case of blackouts on the grid. So, and the most important thing as well to consider is, the bigger the application, i.e., the 6 to 8 hour applications, that does have an opportunity to integrate solar and wind as a backstop to the VRB system. So just looking at in terms of the vanadium sort of historical prices, at the end of 2018, as the price intensified due to new rebar standards taking effect officially in November 2018, this did imply higher vanadium demand. Obviously, vanadium prices did increase by a factor of around 6 to 7, in a matter of a year. And this obviously affected, the commercialization of VRBs, and it quickly fell out of favor with the already incumbent lithium-ion battery technology. So this is something to consider as one of the barriers to the commercialization of VRBs. In terms of where VRBs sits within sort of the demand of the industry, the vanadium industry is primarily driven by the application in steel. So particularly in HSLA steel, which is high strength low alloy steel, that constitutes specifically long steel products, making up for about 85% of vanadium demand. The two other more mature applications of vanadium are in non-ferrous alloys and in chemicals, which constitute for about 5% of consumption in 2019, and the remaining amount, less than 1%, is for VRB. So we definitely see that the potential for upside, starting from a very low base, is significant. That is obviously taking into consideration price sensitivity for the raw material of VRBs from vanadium is something that needs to be considered when looking for the outlook for demand in VRBs. We see that in terms of the future outlook for VRB commercialization under our base case scenario, we see that as a result of the price spike that happened at the end of 2018, the large project of UET and Ronco Power in Dalian, which did consume a significant amount of vanadium, was unfortunately went offline. So this is expected to operate far below its new plate capacity, even within a low price environment. So we see that the next 5 years for VRBs will mainly be heavily into developing a strong, robust and flexible legislative framework that is profitability enabling for a lot of VRB manufacturers, and also the cross-industry collaborations that will take place. So we see that a 5-year timeline is a reasonable time for the VRB industry to sort of bring down its overall capital costs. We see that this is pretty much a reasonable time frame to see that VRBs will uptick in vanadium demand during the second half of the next decade, 2020 to 2030. What's interesting as well in terms of project installations, we see that China, the USA, and Germany are current market leaders. There's also interesting cross-industry collaborative partnerships across the market spectrum. We're seeing, either cross-border flow projects between the USA and China that's been commissioned. Obviously, VRB Energy have commissioned their recent 40 megawatt hour project in China. We also have Sumitomo, who are a long-standing VRB manufacturer. They do have a recent project that is ready to be installed, which is 51 megawatt hours, expected to come online by 2022. We also see an interesting Red Tea and Avalon merger as Infinity. They will cover the entire market spectrum. They do cover pretty much the VRB manufacturing aspect and the sort of technological application. So it is a unique partnership for the industry going forward. And obviously the significant announcement of a 3 gigawatt hour manufacturing facility in Saudi Arabia between SABIC, the chemical subsidiary of Saudi Aramco, and Schmidt, a German technology company. So essentially, I wanted to, outline some of the key arguments for VRBs and their commercial applicability and what the outlook looks like in terms of, from a cost standpoint and a commercialization standpoint and where it is within the industry. And so essentially, we at ROSKILL, we conduct vanadium research. The research you saw here forms the basis of the market research in our vanadium report, and we publish annually, which comes with 10-year forecasts. The most recent report published was in June, which comes with quarterly updates, which will incorporate the ongoing market research into our subscriptions. As you can see, the contact details are below if you are interested in such research. We also have our upcoming South Africa conference that will happen at the beginning of next year during the week of the Indaba. This will obviously cover key steel alloy raw materials, including vanadium as well as chromium manganese. So I hope that was a clear and insightful presentation for you all. I'll hand back over to the moderator, and thank you.
Agradecemos ao Sr. RAMSEY YAVUZ da ROSKILL pela sua apresentação.